Good afternoon. My name is Lorenz. I'm the director of Scientific Force Laboratory, and I'm very pleased to start the Spring 2026 SAFL Awards ceremony. We have a very exciting full program, and today we are going to give the award for the present award for Stefan Award, followed by Silberman Fellowship. There are two winners for Silberman Fellowships, and then followed by a Song Award, and at the end it will be our Straub Award. So therefore we have back-to-back a lot of award presentations, a lot of congratulations, and also a number of presentations for that. So let's get it started. And our first award to present is Heinz Stefan Award. And I am inviting Dr. Chris Ellis, who is a former student of Professor Stefan, and Dr. Chris Ellis, you probably, I guess everyone knows, except probably very, very new students. And I'm not sure about the people online. So Dr. Ellis, he was SAFL's research staff for many years, and he was researcher 7, the highest technical level one can achieve for that, and has supervised and helped so many students and worked with researchers. And he was lucky enough to be a student of Professor Stefan, and he's going to share with us about it.
I'm going to keep this brief. First of all, I want to thank the Damanatharan family who actually established the fellowship in honor of Dr. Stefan. Heinz Stefan retired in 2011, and he died last November at the age of 89. The bullet points of his legacy include the fact that he inspired and mentored more than 100 master's and PhD students. He authored over 240 referee journal articles and numerous reports, review articles, book chapters. He gave more than 60 invited lectures and taught abroad in France, Germany, India, China, and Brazil. He received a number of awards, including the International Water Association Founders Award, Best Paper in Water Research, the ASCE Hunter Rouse Award, and the University of Minnesota's Distinguished Graduate and Professional Educator Award. Over the years, I talked to him lots, and some of the most interesting stuff I learned about him was from his childhood. So I thought rather than go on about all the accolades about his academic work, thought I would recount a few of those. He was born in Bohemia, which is in the Czech Republic, in 1936 during the Nazi rise in neighboring Germany. The Czech Republic was occupied by Germany in 1938 and again in 1939. Heinz had 3 uncles conscripted into the German army at that time. They all died in the war. His father was spared because he had a gimpy foot from childhood. The Russian, toward the end of the war, the Russians occupied that area. And in the spring of '45, he remembered collecting fish floating on a lake that the Russians went fishing with hand grenades, remembered his mother and other local women hiding from the Russians to avoid being molested, which is to say raped. In the spring of 1946, all the German-speaking population in Bohemia, about half the population of 3 million people, were expelled, initially to former prisoner of war camps in Poland by rail and cattle car, but they were turned away at the Polish border. Instead, they were sent to Bavaria, which was in the US-occupied zone in Germany right after World War II. His mother spent those few months of this exile from their home in the Czech Republic, begging for food for her family, including Heinz's 1-year-old brother, Gernot. They were often hungry and they just barely survived that that short period. In June of 1946, his father got a teaching job in Lower Franconia in central Germany, and the family lived there until Heinz went to the University of Munich in 1954, which was the year I was born. He received his doctorate in engineering in Toulouse, France, 1963, and he wrote his thesis in French. Came to SAFL, to the St. Anthony Falls Hydraulic Laboratory at that time as a postdoc in 1963, and he joined the University of Minnesota faculty in 67. So that's a short blurb of his younger years. And on a personal note, I want to end this with, I have benefited beyond measure from Heinz's journey to America so long ago, and from all the many students from other countries, many of whom stayed to become U.S. citizens and long-lasting friends during my 40-plus years at SAFL. Our country is so much more because of their journey. We should take a moment to reflect on this and embrace our immigrant neighbors rather than demonize them. Many years during our monthly lunches with Heinz and a few of his students, he'd reflect on his childhood during the rise of Hitler, and he was often worried about the possibility that history could repeat itself.
Thank you, Dr. Ellis. Okay, that's wonderful introduction. Okay, and next, I am going to introduce the winner of the Stefan Award this year. Okay, so the student's name is Saswata Basak, and he is originally coming from India, and he earned his bachelor's degree in chemical engineering from the Jodhpur University, and then he went to IIT, okay, Bombay, okay, to earn his master's degree, okay, and then he joined University of Minnesota in January of 2022. Okay, yeah, okay, yeah. So. Well, okay, so he did a wonderful job for his master's degree. Okay, so when he contacted me, okay, he already had the first author JFM paper published. Actually, from his master's thesis, he had 3 JFM papers and 1 Journal of International Multi-Phase Flows. Okay. And after he got here, somehow he became very interested in developing numerical methods. Okay, yeah. So he had a paper published in Journal of Computational Physics. That is the top journal for numerical algorithms in CFD. Okay, and last night, okay, his second JCP manuscript just got reviewed back, and so today is a really good time for him. And then that was very favorable reviewed. Okay, and meanwhile he had another manuscript also finished yesterday, and then also there's a GRL paper co-authored on the review now. Okay, yeah, so I better stop here and then invite Saswata to come to the podium and. Presentation first or award first? I forgot. Can anyone remind me? What's the order? Give an award first? Yeah. Okay, or whatever it works. Okay, we can ask him to give a presentation first to see whether he really earned this award. Okay, or we can give him some motivation first. Award first. Okay.
I would like to thank Professor Shen and the SAFL Award Committee for considering me for the Heinz Stefan Fellowship. So today I'm going to talk about bubbly flows and associated physical processes in the ocean environment. But before that, I would like to pay my respect to Professor Heinz Stefan. Professor Stefan is a giant in water quality modeling and environmental hydraulics, and his lifelong research has inspired scientists and engineers all across the globe. And we are deeply grateful to the Dhamotharan family for establishing this fellowship, honoring Professor Stefan's legacy. And Personally, as a young fluid dynamicist, this fellowship means a lot to me, and I'm inspired to work on, devote my research to understanding and solving environmental problems. So today, I'm going to talk about bubbles in the ocean. So this picture represents different complex processes that occur close to the air-sea interface, and bubbles take part in almost all of them. So it starts with breaking waves. Waves entrain bubbles, dense plumes of bubbles in the upper ocean, where the sizes of bubbles typically range from a few centimeters all the way down to micrometers. And during this process, bubbles mediate the transfer of atmospheric gases, such as carbon dioxide, oxygen, and nitrogen, as well as facilitate the transfer of heat and momentum. Based on the residence times of the bubbles in the upper ocean, they scavenge particulate matter as well as surface active agents, and eventually rise to the wave surface, where they accumulate, forming sea foam, which we usually see as white caps on the ocean. It's also important for the albedo, the net albedo. After that, the bubbles burst and they form sea spray aerosol, such as jet drops and film drops. And these aerosols are important carriers of organic matter, marine biotoxins, as well as cloud condensation nuclei. So as you can see, to model air-sea exchange processes accurately, we need to consider the effect of bubbles. So today I'm going to briefly give an overview of the numerical tools that we have been developing in our group to study bubble creation physics, as well as take into account the different factors that influence the number and sizes of bubbles in the upper ocean. We use high-fidelity direct numerical simulations of breaking waves and bubble formation. So this is an example of a simulation using around 8.6 billion grid points, where we can resolve bubbles all the way down to around 300 microns. You can see that initially the wave breaks and it entrains large air cavities, which quickly fragment under the turbulent flow field and yields a plume containing bubbles across a wide range of sizes. So we use novel post-processing tools to analyze this complex data from our simulations. And one such example is our bubble tracking algorithm. So this is a parallel algorithm which uses information on bubble size, position, velocity, and shape to monitor individual bubble events, which can be classified into continuity, fragmentation, which can be binary or non-binary, binary or non-binary coalescence, entrainment, as well as bursting. So this is a powerful tool to investigate bubble creation physics. I'm showing one such example here. So this is an air cavity, a deformed air cavity, which is entrained during the initial stages of wave breaking. And this air cavity, under the influence of gravitocapillary instabilities as well as turbulent eddies, will fragment into multiple bubbles of different sizes. And we can use our tool to precisely track the complete course of this breakup process, and also find the number and sizes of the bubbles produced, as shown in this graph here. In this graph, like each node represents a child bubble, and the colors are the mechanisms of creation. And another such example would be a genealogy graph, such as this, where by constructing these graphs, we trace back the origin of any bubble present at a given time instant. Here, similar to the graph shown in the previous slide, the nodes are represent parents from preceding generation, and the colors are the different mechanisms of creation. Another important factor that influences bubble dynamics is the oceanic salinity. So these are experimental footages of breaking waves, laboratory scale breaking waves in freshwater and saltwater, performed at Scripps Institution of Oceanography. As you can see, with the addition of salt, there is a drastic increase in the number of bubbles. And the main reason for that is that salinity suppresses bubble coalescence. And what salt ions do is they delay the film drainage between contacting bubbles by Marangoni forces, and we have developed a numerical framework that can capture such effects, where we can precisely control bubble coalescence behavior in our numerical simulations by coupling our framework with subgrid scale film drainage models. Why subgrid scale? Because the film thickness is of the order of nanometers, and we cannot resolve everything on our grid because it's a multi-physics and multi-scale phenomena involving other effects such as van der Waals forces, as well as salt-induced Marangoni effects. And this framework is very useful to also capture the formation of sea foam, as you can see in the inset here. Some of the other frameworks that we have been working on is our bubble-mediated gas transfer in a breaking wave, where we can also capture local volume change effects and dissolution due to interfacial mass transfer. And currently we are also studying the effect of surface active agents or surfactants on breaking wave dynamics and bubble creation. And for that we have developed a novel numerical method to compute Marangoni forces. With this, I'm going to conclude my talk, and I'm going to thank our team, Professor Shen, Dr. Grandin, and Dr. Dale Stokes, our collaborators at UCSD Scripps. I want to thank Umberto, with whom I'm actively collaborating on many of these topics, Sai, Dr. Chiang Gao, Dr. Han Liu, Dr. Anjing Xuan, and all my other lab mates. I would also like to thank ONR and NSF for funding support. Thanks for your attention. I'd be happy to take any questions.
Thank you, Saswata. Okay. And we have time for 1 or 2 questions. Okay. Anyone? Yeah. Professor Wickett.
Thank you so much for sharing what you're doing. I was curious, when looking at the saltwater versus freshwater bubble densities and the foams, how much the bubble rafts change the rheology of the water and therefore are changing some of these properties that you're investigating.
I haven't looked at this. That's an interesting point, but I haven't looked at this closely.
Okay, yeah. Thank you. Other questions? Okay. Otherwise, let's move on with the program. Okay. And next, I'm going to invite Professor Emily Fairfax, who just came back from Hollywood. You probably know about that, right? Okay. And so she's going to introduce the Silberman Award first.
All right. Thank you. So yes, if you haven't seen Pixar's movie Hoppers, you should. It's about beavers, and it is related to the winner of our award today. So I am introducing the Silberman Fellowship. Edward Silberman was a director of St. Anthony Falls Lab. He was a civil engineer. He was an interdisciplinarian. He worked on a lot of different facets of water and how it works, and importantly, water resources. Thinking about where is water, do we have it when we need it, how do we get it there? Today, as climate is changing, this is an ever-pressing question. Do we have enough water? And unfortunately, climate change isn't affecting everywhere equally. As you go further and further north, the effects become more pronounced. So the winner of today's, or one of the winners, I should say, of today's Silberman Fellowship has been investigating just that. How do we keep water where we need it when you go pretty much as far north as you can up towards the Arctic Circle? So Alyssa is one of our winners, and what she's been studying is how do nature's engineers help us manage our water resources in the Kenai National Wildlife Refuge of Alaska. This is absolutely an engineering challenge, and if you haven't spent much time in Alaska, there's not a lot of human engineers up there because there's not a lot of humans up there. It's a very wild and large landscape, and so thinking about how we can utilize that natural engineering that beavers do is helping us understand how to prevent drought, how to re-wet peat that has burned, how to prevent more carbon loss during wildfire, and how to keep the water there when we need it. So I'm super proud of Alyssa for all of her research. She joined my lab in 2024 and came in with about a year of grad work under her belt already and absolutely hit the ground running. Alyssa did over a month in the field last year with more mosquitoes than I think any of us have encountered in our lives up in Alaska and Wyoming and Minnesota. She has navigated extremely difficult environments to collect the data she needs and then seamlessly blends that fieldwork into her remote sensing and her modeling efforts. She, like Silberman, is an interdisciplinarian. She is clever, she is a leader, and she is just now beginning to carve a path forward that I have no doubts will be equally acclaimed. So I'd like to invite Alyssa up to accept this award from me, and then to give her little talk about our favorite engineer, the beaver.
All right, thank you so much, Emily. As Emily mentioned, I will be presenting my research, Burning in the Boreal, the role of beavers in the Kenai National Wildlife Refuge in Alaska. So I just wanted to start off with some thanks. Thank you again to my advisor, Dr. Emily Fairfax, and to the Fairfax Beaver Lab, who has helped me in the field and behind the computer in every single way. Could not have done my research without them. And thank you to the SAFL Award Committee as well. So I want to begin continuing my thanks to the family of Edward Silberman. Just to continue on, as Emily was mentioning, Edward Silberman earned his bachelor's and master's from the Department of Civil Engineering in the mid-1930s and moved on to begin his career here at SAFL in 1946. He then took over the directorship in 1963 after Lorenz Straub. He retired as a professor emeritus in 1981 after a successful career working in fluid mechanics, boundary layers, turbulence and cavation, and water resource management, and is the author and co-author of more than 50 publications. So we were kind of posed with the question of what inspires us, and I thought really far back, I've always been really inspired and questioned nature. I actually wrote a book when I was 6 years old, very proud of it. It's called If a Tree Can Talk, and I basically posed the question is, if a tree could talk, what would it say? And to this day, still trying to figure that out, but instead of looking through what I think a tree would say, I'm looking through the lens of beavers, which are nature's engineers. So my research takes place in the Kenai National Wildlife Refuge that is in southwestern Alaska, down there in the corner. It is about a 2 million acre refuge set aside for protecting animals, wildlife, and really setting aside that land to conserve the area. And so when beavers occupy a landscape, as they do in Kenai, they engage in 3 main forms of ecosystem engineering, which is dam building, tree cutting, and canal digging. This is really important because it slows the flow of water, increases surface water storage, and enhances both lateral and longitudinal hydrologic connectivity, which is really important in the face of climate change, which is affecting Kenai in disappropriate ways. These ecosystems in northern latitudes are faced with warming at twice the average rate, which has then had them face wildfires. So Alaska specifically is projected to have peatland wildfires double in frequency within the next 100 years, which is really scary. It's already being seen in the Kenai National Wildlife Refuge. I had the honor of being able to go out there this past summer with my lab mates and start digging into this research and get on the ground, and as Emily mentioned, go through some really rough terrain and see what this looks like on the ground. So this is just an image of this really beautiful beaver wetland in the middle of a burned peat spruce forest. So you can see all the way in the back, completely burned, all the way in the front burned, but where the beavers are, it did not burn, which is what I've been looking into a lot in my research. I've been using geospatial methods to quantify beaver impact. So aim 1 is kind of figuring out where the beavers are. Where are they and where have they been? So I've been estimating the landscape's capacity for beavers using what is called the Beaver Restoration Assessment Tool, and then moving on to quantify burn severity and vegetation greenness across different vegetation types. Lastly, I've been putting it all together to determine if beaver-modified areas have different greenness patterns than areas without beaver influence. Some initial findings. This is results from my Beaver Restoration Assessment Tool, and this is modeling the capacity to support beaver landscapes. capacity of the landscape to support beaver dams. And so this model gives you two types of outputs. It has historical and existing. So what I've been finding so far is there's been a shift. And so in the past, we've had different regions be able to support at different capacities, and still trying to figure out why, which is really important, why we went out there, getting to go on the ground, seeing what beavers are using to build their dams. In 2019, the refuge faced a mega fire. This fire burned through over 100,000 acres in the Swan Lake in the Kenai Peninsula, which is now known as the Swan Lake Wildfire. And so what's really cool is we can see up in that top corner is where there's beaver ponds, which are those pink little squiggles. The areas did not burn. So I have my color scale at the bottom. The areas that are the darkest have the highest severity burn, all the way to the lightest are low severity to no burn. So we've been finding that beavers have really had an impact in this fire specifically. Like I said, in that corner, that area did not burn, and as you look throughout that fire scar, the areas where there are beaver have the lowest burn severity. And so kind of placing it all together, that's just one aspect of the research that I've been doing. That's at a large scale. And then other aspects of my research look at smaller scales, continuing with hydrology, of seeing if we can input man-made beaver dams into this burn scar to see if we can increase hydrologic connectivity and see if we can use beavers to improve the landscape. And then lastly, looking at how beavers create microhabitats within these larger habitats. Thank you.
So my question is, what are the variables? Like how, when you're looking at photographs, are you looking for edible tree quantities or what are the primary variables that set how many beavers per acre, for example?
Yeah, that's a really important question. So our model, it's widely used in the beaver field. It was developed at Utah State University. And so this model has different types of inputs that we put in. And so first what we're looking at is a watershed boundary. So we kind of define the area that we're looking at. And it takes inputs such as elevation, so seeing if a beaver can actually dam that area. It takes in vegetation type, which has played a huge role here. We've been playing around with the different parameters of vegetation type. It takes in the amount of water, so where the streams are. It takes into account kind of like land use, so who owns the land, is it protected, and also roads, if there's human influence. In the Kenai National Wildlife Refuge, there's not. These are all really remote areas. And then it kind of takes into account water flow. So we have high flow and then low flow, base flow equations.
Thank you. Thanks.
Nice work. So the beavers, so fire severity relates to where beavers have dams, and the first thing that comes to my mind anyway is they impound a lot of water, so everything's wetter. But what else is involved? I mean, are there other things, the type of vegetation or other aspects of those ecosystems that are resistant to fire severity?
Yeah, definitely. You mentioned a great key point is that these areas are so wet they don't burn. Something Emily mentions a lot is you can't really start a campfire with wet, soggy sticks, which is essentially what these wetlands are. They're so wet and their water spans out as well. And still kind of digging into the other factors. That's a large part of this research is understanding how these beavers are impacting. Is it the vegetation? Is it the landscape? Kind of seeing what it looks like. So that is still a work in progress.
All right, let's thank Alyssa again.
For the second award winner, I'm inviting Professor Michele Guala to come here to introduce the winner.
All right. Thank you very much, Lian. Thank you all. Thank you for the support. I'm happy to introduce to Roozbeh Ehsani. Is a PhD student, almost finishing. Roozbeh has been a great student. I'm really happy we've been working together on turbulent boundary layers and especially on how to build up a turbulent boundary layer, a synthetic turbulent boundary layers, essentially from the ground up. The idea was how to essentially set a number of rules, experimentally validated, so we can model uniform momentum zone, shear layers, vortices, and start to build up a synthetic field that resemble all the statistical properties of turbulent boundary layers. Roozbeh has been working at the interface, essentially between fluid mechanics and data science. I had a number of students winning the Silberman Award, and they all did great things. So no pressure, whether you will be in academia or in corporate America, you will do great. So Roozbeh, congratulations.
Thank you very much. This is Roozbeh Ehsani. I'm PhD student studying PhD in Department of Civil Engineering under the supervision of Michele Guala. And today I want to talk a little bit about my research project with the title of the stochastic modeling of rough wall turbulent boundary layer. But before that, I want to thank SAFL community and Silberman family for providing this prestigious award and selecting me as a recipient of it. Also, I want to thank and acknowledge my supervisor for his unconditional supports. And I want to appreciate my wife for her presence throughout this year. All right. It's not going. Oh, okay. There are lots of phenomena, transportation, and mechanisms are happening due to existence of the fluid flow. For example, in river, we have microorganisms or organisms that are transferring by the water, or in the air, we have a transfer of the pollutants, or we have flight of the airplane or fighters due to existence of the fluid flow around its wing, or energy generation, or snow transfer. All these phenomena are happening due to presence of the fluid flow. But the question is, if we want to study this phenomena, what do we need for that studies? To study this phenomena, velocity and the pressure of the fluid flow is important. So, to study them, there are lots of different methods and approach, like analytical solution or computational modeling that boils down to solving the Navier-Stokes equation, or experimental studies, and the last but not least is data-driven modeling, which is a hot topic these days for fluid dynamics. But the main challenge of data-driven modeling is the generalizability of the model across different flow conditions. And what do I mean? I mean, for example, you have a model that is trained for 7 meters per second turbulent boundary layer flow, which is a flow over a flat plate. But we cannot use this model to simulate, for example, 10 meters per second turbulent boundary layer flow. Why? Because all the dynamics of the flow, that is, the model is trained, is based on the 7 meters per second, not based on the 10 meters per second. So what we should do to overcome this challenge, we need to find universal structures that is common across different data set that we have, and then model them. So the purpose is to find these universal structures. And for data-driven modeling, guess what? What do we need? We need data set for data-driven modeling. The data set that I use is wind tunnel data set and atmospheric surface data set that is covering wide range of Reynolds number. For wind tunnel data set is the order of 10 to the 4, and for atmospheric surface layer is 10 to the 6. So the studies of turbulent boundary layer shows the existence of coherent structures that we can see it here with in blue bubbles-like shape, and the existence of this structure in the flow that is moving with relatively uniform velocity, with relatively same velocity, and we are calling them uniform momentum zone. And uniform momentum zone is a self-descriptive zones that are moving with a uniform momentum, uniform velocities. So this is the key that we want for our study, to find uniform momentum zone across different data set that I had, like wind tunnel and atmospheric surface layer, and extract the statistics of those uniform momentum zone and then stochastically model them. I'm not going to talk about the finding UMZs or extraction of the statistics because it's more about the technicality. I'm just talking about the stochastic modeling part. So first, we are going to generate the velocity field, we are going to generate 1D velocity profiles independent of each other. Then in second stage, we are going to reorder all these 1D generated profiles to have correlated 2D velocity field. Then in second stage, we are going to add nuances and detailed structures such as vortices to our velocity field. The result of these studies are 3 JFM papers. The third one is still under the consideration, under the revision, but you can find the rest online. The results shows that the generated velocity field are following the mean velocity profile of the generated velocity field following the mean velocity profile of our data sets, which is also following this log law, famous log law in turbulent boundary layer. And also the spectra of our generated velocity field in comparison with the data set shows that they are on top of each other and follow -5/3 Kolmogorov law. Thank you so much, and happy to take your questions.
Question?
You do the Q&A.
Oh, I didn't get it. Sorry. Question from the audience. I was sleeping a little bit.
Well, if you want to ask him a question. Roozbeh, I have a simple question for you. Having done all this work with the uniform velocity zones, do you have any new insight for us on why the log layer is logarithmic?
Why the log layer is logarithmic? Like why it is following log law?
Yeah,
That the mean
you
velocity-
reproduced it. I just was wondering if there was any,
the mean velocity.
yeah, why should it work out that way?
Basically, the structures, this UMZ structure, they are saying that they are attached to these structures. They are scaled with the Z, the elevation. As the elevation is going up, the size of these structures is also increasing. And basically, Thompson and Prontel said that the log law is because of the structures that are attached to these structures that are scaled with the Z. And this reproduction of the log law, I think it's because we are choosing some structure that are obeying that law, that is following that law, and because of that, it's reproducing logarithmic law.
Thanks.
Any other question? I add one thing. So it's attached at D plus the fact that we have the shear velocity that characterizes basically all the elements that we are including in the flow, from the eddies to the shear layers and so on. So the U star remains a very strong scaling quantity across the entire boundary layer. So that both things are important. Thank you very much, Roozbeh. Thanks a lot. And I'll pass it to you.
So next award we are going to present is Charles Song Award. Professor Song was a SAFL affiliated faculty member, and he was also in the Department of Civil and Environmental Engineering at the LIU. Okay. So he was a pioneer in the research of sediment transport, open channel flows, and cavitations. And especially he pioneered in using computer simulations several decades ago to study those problems. So you could see still his work on the posters in the hallway of SAFL. Yeah. And he passed away during the pandemic. And during the pandemic, as you know, okay, a lot of in-person events cannot be held. So therefore, we had the student award ceremony online. Then okay, some of his former students watched the award ceremony. Then he came up with the idea of establishing a student award in honor of Professor Charles Song. So thank you so much for all those former students of Professor Song. And so therefore, okay, we had this new award several years ago. And when this award was established, then it was stated this award will be given to a SAFL student, and especially with a focus on international student. Okay. The reason is because Professor Song, he was an immigrant himself. Okay. And in his education and research career, he paid special attention to students from abroad. For example, like during his lectures, he would intentionally make the blackboard writing clear and making the speaking slower, so that to ensure that the international students, they can get all the materials. Yeah, okay. So that left a legacy of that. Okay. So with that, I'm going to present this year's award winner. That is Ziyan, okay, and we call him Ryan. Okay, yeah. So Ryan came from China, and he graduated from University of Southern University of Science and Technology of China. Okay, that is a new university located in Shenzhen. Okay, and Ziyan, he joined the university during the pandemic, and probably you all remember how things were at that time. Okay, so therefore, for his first year, actually he was online entirely. Okay, and he was attending a university in U.S. all the way for one whole year when he was abroad. Okay, so therefore, okay, for his experience coming as an international student, that at another level of things. Yeah, so only in his second year as a graduate student, then I got to see him. Yeah, okay. And his research is about the computer simulations, about boundary layer flows. Okay, and he has published papers in GPU computing and also in examining eddy viscosity turbulence models. Okay, for flow over wavy surfaces. Okay, and then okay, his current research focused on amplitude modulation of turbulence and also okay, working on the resolvent analysis of flows over wavy surfaces. Okay, without much ado, let me present this award to.
So, yes, thanks for the introduction, and good afternoon, everyone. And my name is Ziyan, and I'm currently a PhD student supervised by Professor Lian Shen. And today I will give a brief introduction of the topic and study, so which is the numerical simulation and the resolvent analysis of the turbulent flows flowing over the water waves. And first of all, I'm very honored and grateful to receive the Charles Song's fellowship. And I would like to express my thanks to the former graduate student who helped to establish this fellowship to honor Professor Song and to help the student, graduate student at SAFL. And it is special, meaningful to me, and to be connected with Professor Song's legacy of research excellence, kindness, and collaboration and inclusion. And this fellowship caused me to contribute more to pursuing my research on fundamental fluid mechanics, and also make steady progress towards my PhD study. And here is a brief introduction of the study I am doing, so which is the turbulent flows over progressive monochromatic surface waves. So the key point is that the instantaneous velocity field can be actually decomposed into three parts. So the one is the mean part. The second is the wave coherent part, which is directly correlated with the underlying wave. And the third part is the turbulent fluctuation part, which is more turbulent, chaotic part of the flow. So my research is mainly focused on the third part of the flow, which is the turbulent fluctuations. So I'm starting to understanding the turbulence and also research how it's affected by the waves. So, and especially, we found that the turbulence can actually be modulated by the waves through the process we call amplitude modulation. And we also did some work about the model-based analysis, which is flow K-Fourier resolvent analysis. We'll talk about that later. And so as we, from the previous slides, we talked about the wave-induced velocity, which is separated by the linear triple decomposition. But even after we remove the wave-induced part, the remaining turbulence is not still completely independent of the wave. It still carries some wave signatures, but it is in a nonlinear way. So we describe this phenomenon as the amplitude modulation. So we can see it from looking at the instantaneous turbulence signal. So this is stringwise velocity fluctuations. So it shows the stronger spikes at the leeward side of the wave crest. So that is this feature is also wave phase dependent. So we can look this phenomenon more clearly by extract its envelope using the Hilbert transform. And by extracting the averaged envelope of it, we can see a very clear a periodic pattern occurring here. So which is also like correlated with the underlying water waves. So the key message here is that the wave is not only generates the wave-induced motions, but also it modulates the strength of the turbulence itself, which is a nonlinear effect. So besides the amplitude modulation work, we also use a resolvent to study the wave effect on the turbulence. And the basic idea is to view the turbulence as a feedback loop, so which is a linear system is forced by the nonlinear interactions. Among all the responses, the linear system amplifies some of them more strongly. The most amplified response tells us the dominant flow structures. For wind-over waves, we build the wave effect into the linear part of the model, so we can examine how the wave changes the turbulence response. At the top figure, for example, we compared the dominant vertical velocity mode from the slow wave to the flat wall. We can see the turbulent mode is actually modified by the wave, so the mode shape is changed. And more importantly, at the bottom figure, we show the phase variation of the turbulent intensity. So here is a prediction of our model, and this is LES simulation data we got. So you can see the prediction agrees really well with the LES result. So this gives us a reduced order framework that can help us to understand and model the wave turbulence interaction. And to conclude, I would like to step back and place our work in a broader context. And so this research is about how to understanding the surface wave modified the turbines, so which is an important part of the air-sea interaction, and also the tools and the analysis we developed here is especially useful for to study the turbulence flows over some more complex boundaries, and it is also connected to some the applications such as the weather focusing and the offshore wind energy. Yeah, so that's all for my my talk here. So I am happy to take any questions and suggestions.
Questions?
Maybe in your first slide, could you go back to the, just curious about the wave and the technique that you're using to separate wave-induced component and turbulence fluctuations, and how should we think about the difference if one was looking at data collected in a wind tunnel or in the field? How would you separate those, or how should we think about where the boundary between a wave-induced fluctuation and a turbulence fluctuation?
Yeah, so this is actually a very good and interesting questions. So so for the specifically for the monochromatic wave, so the technique we are using is called phase averaging. So which is the NAC. So which is essentially like the conditional average with respect to the wave phase. The wave phase is already a known priori because that is the monochromatic wave. But for the like broadband wave, essentially, so the technique we are using is called the Hilbert projection method. So which is also a kind of like conditional average, but that is like the linear estimation of the conditional average. So which need to the linear separation between the wave-induced part. So the wave-induced part is what I can say the regular definition of the wave-induced part is the conditional average respective to some function of the surface wave. Yeah, so that's my that's an answer for the question.
Right, thank you.
Thank you, and congratulations, Ziyan. Yeah. Next, we are going to present the Straub Award. And you might be wondering for students, well, we have a Straub Award once a year, and that is the winner is selected from all around the world. So how was that selected? Okay. Well, there is a award committee. And the committee members are top experts in the area. So to give you an example, there's one time I look at all the list of the former committee members all the way since the 1960s. Okay. Then there was a name, Heinz Einstein, so son of Albert Einstein. Okay. So he was on SAFL Student Award committee for the first 16 years for that. Okay, yeah. So, well, today I'm going to invite the current committee member from University of Minnesota, Professor Michele Guala here, okay, to introduce the award to us and to describe to us, share a little bit of secret about how the award winners are selected.
Thank you very much, Lian. Thank you all. So yeah, it's an honor to represent UMN and SAFL in this committee. And I would like to thank also the two other members of the committees, that are Paola Passalacqua, who's a professor in UT Austin and now is moving, or she just moved to ETH in Switzerland. And the other one is Eli Bouzaid, who's a professor in Princeton. And the idea is to cover most of the expertise in geophysical flows, in honor of Lorenz Straub. He was the first SAFL director, the founding director, and the experiment is in his name, of course. And so the idea from 1966, when the first Straub Award was bestowed, was to celebrate essentially the best dissertation worldwide, or in the broadest sense, right? So what we do is we essentially send emails to all the civil engineering department of famous university and also not so famous university, all alumni, everybody, to stimulate a professor to nominate their student. And so we already, and the nomination is requires a little bit of work, so the students that are nominated are already very much pre-selected. And then we have a committee. Eli is an expert in atmospheric boundary layer. Paul is an expert in landscape dynamics and morphodynamics. I'm as a turbulent boundary layer guys in between the two, so we can cover pretty much from the sky all down to the stratigraphy. And the idea is we receive all this dissertation. And one important thing is they cannot be from University of Minnesota. Right, so our student cannot win the Straub Award, but we have a first pick on who's the best student winning the Straub Award. So for the winner of this year, I introduced Judy to introduce it, and thank you all.
Thank you. Hi, everyone, and it's my great pleasure to introduce the recipient of this year's Straub Award, Dr. Rachel Schaefer. I have been following Rachel's work for many years since she joined Professor Heidi Neff's lab, where I was so fortunate to also graduate from. I was very excited when I learned 2 weeks ago that Rachel is a recipient of this prestigious award. And so Rachel grew up in New Jersey, and she received her bachelor's degree in civil engineering from University of Delaware, where she developed a strong interest in coastal engineering and a nature-based solution. Afterwards, she joined Professor Heidi Neff's lab and received an SF graduate research fellowship. Her research combines laboratory experiments, field research, and a numerical approach to study the interactions among seagrass, wave currents, and sediment transport, with important implications for carbon sequestration and wave damping. After she received her PhD, she started a postdoc research for the US National Park Service. She's now a research engineer in the catastrophe modeling industry. So I'm very looking forward to seeing Rachel's photo in our SAFL library. And today she will talk about seagrass emotion, hydrodynamics, a driver of coastal ecosystem services. So without further ado, please join me in welcoming Dr. Rachel Schaefer in receiving this award.
Thanks so much. My name is Rachel. I'm really honored to be here, to be nominated for this award and selected to receive it and to talk to you today. I've met a lot of really interesting people. This lab is doing a lot of really cool work. I'm grateful for the committee and for Lorenz Straub for all the work that he's done in developing this laboratory. So today I'll be giving you an overview of my dissertation that focused on seagrass hydrodynamics, starting by introducing you to what seagrass is. I think this poet, Erasmus Darwin, put it best when he said, "Stretched on her mossy couch in trackless deeps, queen of the coral groves, Zoster sleeps, her silvery seaweed matted round her bed, and distant surges murmuring o'er her head. High in the flood her azure dome ascends, on crystal arch and crystal columns bends." You can see seagrass swaying in the water here. They are they're flowering plant species found on every continent except Antarctica, consisting of bundles of flexible leaves, also known as blades, that connect down through rigid sheaths into root and rhizome systems. So generally found in shallow coastal areas, requiring some level of salinity. Seagrass meadows provide many different ecosystem services, the total global value of which has been estimated to be very high, roughly 10 trillion US dollars per year. And this includes habitat for many valuable species, such as those fish you saw on the previous slide, sediment stabilization and erosion reduction, as well as carbon sequestration, wave damping, and water quality enhancement, to name a few. A lot of these ecosystem services are enabled by the physical interactions of the seagrass with its environment, which involves the hydrodynamic drag force, which I'll return to in a moment. Just to give an example, coastal vegetation, including seagrass, is estimated to have reduced damages from Hurricane Sandy in 2012 by over $600 million, such that an improved understanding of meadow hydrodynamics extending from seagrass to other species can help us inform our ability to incorporate vegetation into flood and risk management, for example. However, unfortunately, seagrass are threatened by climate change and human activities, expanding populations, overfishing, warming sea temperatures, rising sea levels, and eutrophication. These inspire people to design projects to restore seagrass back to their previous populations. And there are many different ways you can go about designing such a project. Unfortunately, the global success rate of these projects is around 30 to 50%, lower than most other ecosystems. And this is partly because you need a lot of understanding of the local conditions and the hydrodynamics in order to maximize the success. And ultimately, you might want to design your project to maximize the co-benefits, the ecosystem services provided, such as flood risk reduction. So overall, my dissertation addressed a few primary research areas, including how seagrass meadows can reduce wave energy under realistic conditions they might experience along coastlines, both waves and tidal currents. And what role does the flexibility of those leaves play? How does a meadow affect turbulence and flow structure? And how can we essentially relate hydrodynamics to the carbon sequestration ability of a seagrass meadow and improve our ability to account for that? And as part of that, how about a meadow that's kind of shifting around in time and not constant in the same spot? So I kind of addressed these different questions from multiple angles. First, using laboratory experiments. Shout out to Dr. Yang. This is the same, I did work in the same lab she did, using a variety of sensors and flumes, some simple numerical experiments, which I'll mention in a moment, and field experiments. And so none of these methods can tell the whole story by themselves. It's important to look at things from multiple angles, especially since we're dealing with real ecosystems. You know, by combining these multiple methods, perspectives, we can capture both controlled processes and real-world complexity. Now let's go back to that hydrodynamic drag force I mentioned. That can be a driver behind a lot of these ecosystem services. And what I mean by that is a drag force that's generated by relative motion between an object and a fluid. Here is a common equation that's used where it's dependent on the area of the object facing the flow direction, as well as the difference in velocity between the object and the flow, such that if your object is not moving, this simplifies to the flow velocity squared scaling. So you can kind of think of this visually in your head as imagine a leaf on a tree fluttering under a light wind. It's curling up a little bit relative to no wind conditions. And then the wind speed increases. The leaf starts to curl up even more and flutter faster. And now you have really strong gusts of wind. It's curled up about as much as it can be, trying to protect itself, kind of trying to follow the wind flow as much as possible. And we can call what it's doing reconfiguration. It's reducing its area, A, in this equation, facing the flow, and it's also increasing its own velocity to try to reduce its relative motion and the drag force it experiences to improve its survival, and so it doesn't get torn off this tree. So how can we relate? We can extend this sort of reconfiguration idea to flexible seagrass plants, but then how can we relate that to wave damping, for example? Well, the time averaged rate of wave energy dissipation at a point in space is the work done by the drag force, caused by the presence of that plant. And then we can translate this into a spatial change in wave height that you would observe in a physical seagrass meadow, where if the meadow is long enough and dense enough, you will see the wave amplitude decreasing across the meadow with a constant water depth. However, under those waves, the plants are moving, they're flexible, they're following the oscillatory wave phase motion. Here's a simplified cartoon of example seagrass leaf motions under the wave phase, where at each point in the wave cycle, it takes on a different posture. But how about currents? Seagrass meadows are found along many coastlines with strong tidal amplitudes. When you have a current, when your time average velocity is non-zero, the seagrass will take on a time average bent position, and now it will oscillate about that average bent position, on both of which affect the drag forces that are generated. So many people have done studies on the effects of waves separately from the effects of currents, but it's important to try to consider some other interactions. They can get pretty complex, so my dissertation covers only a few of them, but overall I was interested in giving some insights in how the addition of current impacts wave damping in a flexible meadow. And my primary observation was it depends on the stiffness of the plant, of the leaves, how much it resists being forced over by the current or the waves, on the speed of the current relative to the wave orbital velocity magnitude, and on the relative directions. I have 2 papers about this. I'll go into just a general overview of how I approached this. So I did a series of laboratory work connecting seagrass dynamics to wave damping, and then kind of supplemented that using simple numerical modeling, where I created an idealized seagrass blade clamped to the seabed at the bottom, and discretized it into space along its length and in time across multiple wave periods, kind of stepping through, estimating a force balance at each of those points. Again, based on, and tested a variety of different wave and current velocity combinations, as well as plant stiffnesses. And here, for example, I'm showing an animation of the motion of a blade across a wave period under just an imposed wave condition, 0 current velocity, and then that same condition, but adding in a current, with the arrow direction and magnitude representing the relative velocity highlighted in blue in this equation, such that during the flow reversal phase of the wave, it's kind of counteracting the following current, resulting in overall reduced relative velocity and therefore reduced drag, ultimately meaning for this condition, adding in a current reduces its ability to dissipate wave energy. But other factors are also at play. I won't get into those in too much detail today, but we can use these relative velocities, integrate them to find the work done by the drag, and then translate this into changes in wave amplitude to sort of extrapolate across many different conditions. So I've talked about some leaf scale dynamics in terms of wave energy dissipation and drag. How about how that relates to other ecosystem services? Next, I will talk about seagrass carbon sequestration, meaning the ability of seagrass to lock away carbon, essentially carbon dioxide, for long periods of time. Now, in order to kind of think about this, we should consider seagrass meadows along a continuum of other coastal ecosystems. Typically, you might have a terrestrial forest sloping down into a salt marsh, then a mangrove, maybe a mangrove system, depending on where you are, a seagrass meadow, and then possibly kelp or coral. So you might have runoff of carbon from various sources, from your forest, salt marsh, mangrove systems that reach the seagrass bed. Seagrass itself is generating dead plant material, and there's also animals and algae living in it that are also dying and decomposing. Some of that carbon is transported out, however. we believe that the seagrass meadow creates an environment that enhances the burial of those particles that I'll talk about in a moment. Such that it's estimated while seagrass meadows take up about 0.2% of the ocean floor, it's estimated they account for about 10% of organic carbon burial in the oceans. In other words, they have a higher per unit contribution to carbon sequestration than bare sand. However, there's a lot of uncertainty here. High variability between different species, different meadows, different locations, and even within the same meadow itself. And this complicates efforts that people have been trying for using carbon credits to fund those restoration projects I mentioned. They're expensive, they need funding sources somehow. You can apply for carbon credit by saying, hey, if I implement this project, it will store more carbon than would have been stored without this project. But it's very hard to quantify and prove that. So hopefully some of this work can help contribute. So let's zoom in on the seagrass meadow to get a better idea of why it might be better at sequestering carbon than bare sand. So we have this series of carbon particles moving in on a tide, these indicated by these brown dots. And they're moving slower within this seagrass meadow, that's waving here, than above the seagrass meadow. And as they move slower, they're allowed to settle down to the bed and bury themselves. Lower chance of being resuspended or decomposed, especially with a low oxygen environment at the surface of the seafloor. And so a better understanding of these dynamics, again, is useful for carbon credit verification, as well as overall a better understanding of climate change risk reduction. So overall, we believe that when water slows, carbon stays. Looking at this from a side view, you can imagine a vertically uniform velocity profile, a tidal current coming toward a seagrass meadow, stirring up some carbon particles at the bed, some carried along the water column. They come from different sources, plant material, terrestrial, and they come with different signatures. But once it hits the seagrass meadow, these blades, through the drag force, kind of drain momentum. And so the water wants to take the path of least resistance. So more water will be directed above the meadow than within, creating this sort of low energy environment that can provide shelter for those fish that I mentioned, but also help reduce the momentum of those particles, allow them to settle down and bury, again, in this low oxygen environment within the seagrass meadow. Such that if you take a measurement of carbon outside the meadow versus within, you might expect to see higher carbon in the meadow. However, let's say you take another measurement at someplace else in the meadow. Would it be the same as your other measurement in the meadow or different? And it's hard to say. Another way to look at this is in more wave-dominated sites where as seagrass sort of reduces wave amplitude, that reduces the wave orbital velocity magnitude, such that you might expect to see a gradient, a spatial gradient in carbon sequestration, keeping everything else the same. So in my dissertation, I looked at a few different scenarios, more tidal current dominated, more wave dominated, where kind of trying to understand how the spatial variation in sediment organic carbon content and accretion rates relates to this hydrodynamics, either through wave damping, sediment circulation and supply, or other factors. And overall found that, yes, vegetated areas definitely seem to have higher carbon content and accretion rates than the bare surrounding areas. And we found patterns related to sediment supply and wave damping that matched, my previous modeling efforts. However, one field site we looked at, which was a patchy meadow, this was not the case. So overall, we found that the transport and deposition of carbon depends on turbulence. But how about that patchy meadow? What was going on there? So we kind of tried to dig deeper into why this patchy field site on the coast of Massachusetts seemed to have very similar sediment carbon across all of the patches we measured and the bare areas, except one patch in particular. Our hypothesis was that we would see higher sediment carbon in the patches than the bare areas because of the low energy regions within the patches, which enhances sediment deposition. So we wanted to try to explore plausible explanations for our observation. So we turned to grid-based modeling as a tool, a conceptual tool to relate patch dynamics to hydrodynamics. And appealed to percolation theory, which is a simple kind of thought experiment where you can imagine each square in a grid has a chance of being vegetated, green, with probability P, or bare, brown, with probability 1 minus P. And again, meadows don't occur in square grids, and they tend to cluster as they propagate. But this is a possible conceptual tool or framework from which we can consider things. So I'll show you an example of what I mean. When you have P equals 0, you don't have any vegetation. Everything is bare. And then when you start having some coverage, 10% vegetated coverage, P equals 10, you have many, many, many isolated clusters. And as you increase P equals 20 and 30, the number of clusters continues to increase as the space brown area fills up. However, some clusters do start to connect to each other. As you go up to P equals 40%, the number of clusters starts decreasing as more and more of them connect. Then when you hit 60%, in the percolation theory, this is a threshold where you're guaranteed to, on an infinite grid, be able to trace a line uninterrupted from one end of your vegetated patch to the other without ever having to go through a brown pixel. So in other words, there's enough vegetated coverage to cover very large parts of the grid to have constant connectivity. The kind of flip side of that, when your bare coverage is 60%, is that a bare channel is basically guaranteed to cut all the way through your meadow. And if it can do that, that means there's a high velocity region bisecting your meadow. And so, as you continue increasing your coverage, then you get closer and closer to a continuous meadow. So we can try to use percolation theory to relate to our field site by taking advantage of aerial imagery. We combine some drone imagery that we took with historical satellite and aerial images taken during the growing season of our field site. We normalize them so they registered the images so they all represent the same things spatially, and then applied a consistent algorithm to all images that roughly estimates the vegetation coverage. Now, our meadow kind of grew along the coast. It was not a perfect grid, so we tried a few different methods to approximate the coverage, and they all ended up with similar results, essentially trying to calculate the number of vegetated pixels divided by the space in between the patches, and then plotted this value for each of our historical images versus the year of the image, where one year we didn't find any patches, but thought that was, because there was a hurricane and a blizzard that year, but fortunately the seagrass, I think, had enough buried roots and rhizomes to be able to bounce back. But other than that, the average vegetated coverage was about 40%. Sometimes it was higher, sometimes it was lower, there's some uncertainty, but that 40% number might sound familiar. When your vegetated coverage is 40%, you have a high chance of a lot of bare channel connectivity. And when you have these high velocity bare channels cutting through your meadow, it's very hard for the patches to coalesce, to sort of break through that high energy region. However, it looks like there is enough vegetated coverage here that they cannot be completely wiped out. So how about the mobility of these patches? Are they just constant? Well, it turns out if we, in each image, kind of track each vegetated pixel and how long it was vegetated through the previous images, most patches were not persistent for more than 5 years, maybe 10 at the most. So in other words, as we kind of scanned through these images, the patches were constantly shifting around, which could mean that in some years, one edge of a patch was eroding while the other edge was expanding. So, combining some vegetation propagation dynamics with hydrodynamics. And I mentioned that we saw that one patch with higher carbon content than any other measurements. So we paid special attention to that patch, and it had been in the same spot for most of the past 10 years, while all other patches had been there for maybe 2 to 4 years. So This is not, we're not claiming this is the reason for our observations. There's a lot of uncertainty, but one plausible explanation. So overall, it seems like there's some kind of emergent physics-based dynamic stable state, hovering around 40% vegetation coverage, even though the patches are constantly shifting around. This unfortunately means that a patchy meadow, where the patches are mobile, is probably not good at keeping accumulated carbon. And let me show you an animation kind of explaining that more. So I tried to make an animation that's more realistic of vegetation propagation. And we can assume when a pixel becomes vegetated, the carbon level becomes maximum, becomes dark brown here, while the surrounding bare areas have very low carbon, indicated by beige. I'll talk about that assumption in a moment, but over time, we think the patches are sort of shifting around, and once a patch leaves an area, the carbon that had been accumulated there is quickly eroded away due to a combination of higher oxygen environment, higher wave and current velocities, and the greater ability of clams and other critters to dig down into the sediment, bringing down oxygen, disrupting and bioturbating things. While with seagrass there, the roots are kind of blocking them from doing that. However, in reality, seagrass carbon accumulation typically takes about 5 to 10 years to be measurable. So by the time it's accumulated some amount of carbon, the patches might already maybe be moving on. So overall, this constant connectivity of bare areas with higher velocities seem to prevent the patches from coming together, meaning that such a dynamic meadow might not be as good at sequestering carbon as those continuous meadows in more wave or current dominated areas, but still provides many other ecosystem services. This analysis does not account for roots or bacteria or oxygen clams. It assumes vegetation can occur on a grid and involves some stochasticity that might not be super realistic, but it was a conceptual tool and a framework that seemed to provide some insight and was supported by some of the literature. So overall, I've talked about connecting seagrass hydrodynamics to ecosystem services, and talked about a few of the nuances there. You can feel free to read my papers or ask me questions if you want to learn more. But why does this matter? Some key possible applications are that an improved understanding of these processes can inform restoration project design. I worked with someone during my PhD to try a few different ways to use our hydrodynamic models to inform some pilot scale restoration design projects. A lot of them failed for different reasons, like huge waves of mussels getting stuck in the seagrass or getting buried by massive amounts of sediment. It was very hard to predict using our laboratory models. Learned some interesting insights. Maybe this work can also help inform some of the hot debates in carbon credit methodology, how to quantify the contribution of seagrass to carbon sequestration and translate that into monetary value, as well as more generally nature-based solutions for coastal resilience and climate risk mitigation. So I want to thank some of these funding sponsors, as well as my advisor, Heidi Neff, my committee, my lab mates at MIT, and everyone who assisted in my fieldwork and laboratory experiments. And again, thank everyone here for being so welcoming and inviting me here to talk. Thank you.
Have time for several questions. Oh, Chris.
So would I be right in thinking that one very basic outcome and recommendation for you would be that if you were doing a seagrass restoration of a marsh, 60% is the minimum coverage? Is that fair?
Yes, I think you probably want to aim for a pretty high vegetated coverage, both because the higher the plant density, the higher the wave energy dissipation, for example, and all the other, and quieter habitat, lower sediment transport, and also helps it stabilize itself, not let a bare channel connect through even if a little bare spot forms within the meadow, it probably will get filled in pretty quickly because it's not connected to anything. The connectivity, I think, is the important thing. So yeah, aiming for high coverage if possible. Sometimes a site might be too high underneath, and you might need to move to another site. Yeah.
Okay.
So fascinating talk, and thank you for the great visuals. I'm wondering if I noticed on one of your plots, it kind of hovered around an average of 40%. Do seagrass beds need some amount of mobility to survive? Is it like they accumulate too much of a certain substance and then move, or is it purely a hydrodynamic driven?
So if you do have too much seagrass, there's something called sulfide toxicity that can start to accumulate, which can start to be unhealthy for the seagrass due to a variety of biogeochemical processes. That's all kind of dependent on some of the sediment characteristics as well. So you can design your restoration to try to minimize that. Seagrass usually expands either clonally, expanding its rhizome system, or vegetatively, kind of breaking off seeds and hoping it lands somewhere and sprouts. And it can kind of adapt which method it wants to do. Like if it can't really seem to expand outward, it might start to go downward and then horizontally, or just grow more what are known as reproductive shoots to sort of send out flowers. The edges of a seagrass meadow are probably the most vulnerable ones because they kind of getting hit by some of those high velocities. So it might be a little, might have to pay special attention to those, I guess. Good question.
Please, do you have a question?
So in general, are the patchy configurations or the larger meadow configurations more common? Do you have enough observations to know?
Question. I think due to the difficulty of surveying the entire oceans, the full extent of seagrass is not very strongly identified. But I mean, they do have to occur in shallow enough regions for light penetration to hit them. But overall, I think, especially in areas that are most degraded, higher pollution, or areas with very high energy, those have the highest chance of fragmentation, of seagrass meadow not being able to sustain continuous mass. So I'm not sure the relative proportions of patchy versus continuous. Yes,
okay.
That's a good question.
Anyone wants to ask the last question? Okay, Lian. Lian, may you also have your closing remarks?
Thank you so much. It's really wonderful work. Okay, yeah. So I'm wondering if, that's a big if, that is impossible if you will do a second PhD on this topic, what would you envision? What would be the breakthrough in research? Would it be? Okay. I know it's a very unusual question.
Maybe trying to improve, from one angle, trying to improve some of the modeling I did, like in my wave and current interactions. I mainly considered waves and currents kind of in the same axes, maybe opposite directions. So maybe testing more combinations of those, extending it to other kinds of vegetation like kelp or salt marsh. And from the carbon point of view, maybe trying to be more applied, like actually try to create like some kind of propose a more standardized methodology for accounting for seagrass carbon additionality, like how much seagrass contributes to accreting carbon. Because for terrestrial forests, there's a lot of very standardized methodology for quantifying how much this forest project will probably contribute to carbon sequestration. For seagrass, not so much. There's a few proposals, but still debates in the literature. So maybe trying to take a more applied approach and more confident approach and explore that. Maybe there's too much uncertainty, I don't know.
Great, great. And you probably can see I'm trying to steal ideas from you. All right, okay. With this, let's congratulate Dr. Rachel Schaefer again for this really prestigious award. And let me want to add, you probably have been to the Straub library. Okay, so your picture will be on the wall. There's a name plate will be there. Okay, so basically you are stuck with us, with the SAFL. Okay, okay. And with this, okay, let's congratulate all the award winners today. Okay, and okay. Okay. Yeah. So yeah, I conclude the ceremony here today. Thank you.